Good evening everyone. I welcome you to the last problem solving session of NPTEL course combinatorics. So today we'll be reviewing species. We'll look at lot of examples and then we'll solve few problems from class. Okay, so let's start. So first of all, what is a species? Species species is a rule. It is a rule f, so it is we can think of it as a functor or a rule, which it is a rule f which which has which has two types of data. First is that this rule f is assigning a finite set fu for every finite set u. So first of all, to any finite set u, it is assigning some finite set fu. And secondly, if we have any bijection between two finite sets, by bijection means I have one and onto function between two finite sets, so this rule is also assigning a function between fu and fv. And these two assignments satisfy following functorial property. First is this. So if you take any finite set u and if you look at the identity map, clearly identity map is a bijective function. Therefore this rule f will assign some function to identity function. But we want, if species is a rule, we want that this rule should assign identity functions to identity function. That is, if one under script u is depicting the identity function on u, this rule f is sending this identity function to the identity function of fu, because according to the second step, f sigma should go from fu to fu. Therefore the first condition is that f of identity of u is identity of fu for all finite set u. And secondly, we also want compatibility with respect to composition. So suppose you have two composable bijections, that is, you have two bijective functions which can be composed. So we have these finite sets u, v, w, and sigma is a bijection between u to v, tau is a bijection between v to w. Then from data 2, f will assign some function to this. F will assign some function between fu and fv, which will be f sigma. It will also assign a function between fv and fw, which will be some f tau, and it will also sigma. So if sigma is a bijection, tau is a bijection, composition of two function is also a bijection. So this tau or sigma is a bijection. This tau or sigma is a bijection between u to w. So according to our data 2, it should assign some function to f sigma or tau. And this rule, we want this compatibility, that these three functions that f is assigning should be compatible in such a manner, that is, f of composition should go to composition of f. So if f of tau or sigma is equal to f tau composed with f sigma. So we see what is, so if something is a species, first of all, it is a rule f which has two type of data. To each finite set u, it is assigning some finite set fu, and secondly, to any bijection between two finite set, it is assigning some functions. And these two assignments should be functorial in this sense that it should satisfy property A and property B. It should send identity function to identity functions, and secondly, it should be well behaved with respect to composition. And this is an exercise, and if A and B use A and B to show that these assignments f sigma are also bijections. So we don't need to assume it. Property A and B implies it. So what is this exercise saying? So it is not so this rule, species rule, is not assigning some ordinary function. It is assigning a bijection to a bijection. Okay, now to make it more clear to make it more clearer, let's look at some examples. So first, simplest example is species of sets, which will also denote by epsilon. So first of all, if it species is a rule, so first of all we need two assignments. We should assign some finite sets to each finite set, and secondly we should also assign some bijection to some bijection. So how we are defining it? We are sending any finite set u to the singleton u. So we are sending each finite set to a set containing one element, and that one element is the set itself. And then if we do that, so now we have to assign a bijection to each bijection. So suppose sigma is a bijection between u to v. Then we have to, from this exercise we know that we have to assign some bijection. Now epsilon sigma should be some bijection. Now epsilon u is a singleton set, epsilon v is a singleton set, and therefore there is just one bijection between two singleton set. We have no other option but to send u to the we have no option but to send u to v. Epsilon u is a set containing just one element, which is u, and it is so epsilon sigma sends u to v. So now we have done our assignments, and now you need to check a and b are satisfied, and if they are satisfied, we know that this is a species. So it is a very ordinary check. So suppose, like, even if we want to check ordinary check, so let's see if we want to check for 1. So first we have to check a. So a is that epsilon of 1u should be 1 ops epsilon u. So this is straightforward because epsilon of u is singleton u. So it is sending identity function to identity function, because epsilon u is just epsilon u contains just one element u. So u goes to u under this function. So it is the identity function. So we can see that clearly a is satisfied, and b is also satisfied. We have to see. So if we have two functions, sigma u to v to w, sigma tau, now we have to see what is epsilon u to epsilon v and epsilon w. So we have these functions. So we have epsilon sigma. So I'm just checking these two properties for the first example. Rest of them you will check, just to show you how these properties are to be checked. So epsilon sigma, this here u goes to v and here v goes to w. Now if you see epsilon sigma or tau or sigma will go from epsilon u to epsilon w, and it will send u to w. So this function and this function are same. So epsilon tau o epsilon sigma is same as this function. So second property is also satisfied. So we see that this assignment is indeed a species of sets. So now you will check these functorial property for rest of the examples. So first of all, let's discuss the rest example. Now second example is species of K sets. So by species of K set we mean that, so what is it doing? So it is this rule is kind of identifying these sets which have K element. So this function, how it is, and this K is for any integer. K is any integer, non-negative integer. K equal to 0 will also work. So yes, epsilon k, okay, k for k, no, it's for a positive integer we are defining epsilon k. So epsilon k u, so what is it? So it, as I said, it is identifying, it is like an indicator, it is like an indicator function. It is indicating which set has k element. So epsilon k u, it goes to set with single element u if order u is equal to k, and if order u is not equal to k, epsilon ku is empty. So this is the assignment of sets. Now we look at the transport function. So these are also called the transport. So epsilon sigmas are also called the transport function. So in this case, what will be the transport function? So to defining transport function, first, okay. So for defining transport functions, yes. So first is we have a bijection between u to v. So we have two cases. Order u is equal to order v is equal to k. Order u is equal to order v is equal to k. That is, both set are k order. Then we know each of these set have single element. So we are sending the element u to the element v. So this is the epsilon case sigma function, and in case, the second case is when order u is not equal to k or order v is not equal to k. So since it is a bijection, if one of the order is not k, then the other order cannot be k. So these two cases make up the whole cases. So now in this case, epsilon u is empty and epsilon v is empty. So we have no function basically. So this was species of k set. Now third example is species of linear order or linear arrangements. This is also called species of linear arrangements or linear order. Now we are denoting this species by letter L. So what is this species doing? So this species is assigning to each finite set U set of all linear arrangements of elements of U. So if U has k elements, if U has k elements, say U1, UK, then LU is basically type of ways in which U1, U2, UK can be arranged in a line. This is aside. Or you can see giving a linear arrangement. So if you want to, so I'll write it down later nicely. So here is the important part. So so it is assigning any linear arrangement. So by linear arrangement we mean that if U is equal to U1 UK and we have k places, suppose 1, 2, 3, 4 till we have k places. So by linear arrangements we mean arranging these element U1 UK in these seats. So you can see giving a linear arrangement is same as giving a bijective function from 1 to k. That is, so giving a 1 to k, suppose this function is f. So fi denotes the letter in ith position or element in ith position. So LU is basically collection of all bijective functions from 1 to order U. So if order U is equal to k, this bijective function go from set of natural integers less than k to U, 1 to k to U. So it is a bijective functions from 1 to order U to U. So now this is it. This is the assignment of each set. Now we have to give a species. As you see, there are always two data involved. First we have to assign a finite set to each set, and then we also have to describe the transport function. So suppose sigma from U to V is a bijection. Then how should we define L sigma? L sigma is basically, so we have to give a function. L sigma is a function from linear arrangements of U to linear arrangements of V. So now if sigma is a bijective function between U to V, that means each element Ui has a unique image. and every element of V has a pre-image also. So if you think about it, so the intuitive way to define this map will be, suppose U is equal to U1 UK, and suppose our sigma is sending U1 to V1, U2 to V2, and UK to VK. This is our sigma. Now what should we, so given a linear arrangement, that is we have k seeds. So we have k seeds, so we have some linear arrangement here, ui1, ui2, uik. Then what should be the corresponding linear arrangement of V? So we have to use this linear arrangement f, and we have to use this bijective function sigma to give a linear arrangement of V. So intuitively what should it be? So it should be basically, so each element of U is mapped to some element of V. So the corresponding linear arrangement of V, given a linear arrangement f of U, corresponding linear arrangement of V should be, each UI should be replaced by the images, each UI should be replaced by VIs, where VI is the image of UI under this sigma. So this is what our transport function is doing. So L sigma is basically a it is sending f to sigma composed with f. So basically in principle it is doing, suppose if you have two sets A, B, C and D, E, F, and your sigma is A goes to D, B goes to E and C goes to F. So if this is your linear arrangement A, B, C, the corresponding linear arrangement here is D, E, F. If the linear arrangement is A, C, B, if the linear arrangement is A, sorry. If the linear arrangement is A, C, B, so what should be the corresponding linear arrangement? It should be D, F, E. So you see, so if F is a bijection, this sigma OF is also a bijection. So basically we are renaming the symbols. We are renaming the symbols in our linear arrangement. Now the next example is species of permutation. So what is species of permutation? So each set U is assigned set of permutations on U, and by definition permutation is a 1, 1 and onto function from U to U. That is a bijective function from U to U. So PU is collection of all bijective functions from U to itself, and let's say we denote it by S underscore U. So now we have done this arrangement. Now we also have to assign assign a bijection to each bijection. So we have a bijection sigma from U to V, and suppose F is a permutation on U. So if F is a permutation on U, it is a function from U to U. Now by our definition, P sigma should go from PU to PV. So it should send a permutation on U to a permutation on V. So using sigma and F, we want to construct a bijective function from V to V. So we can do it like this. We can send any F to, first we go from, so we have to construct a function from V to V, and we have a function from U to V and V to V. So what do? First we go from V to U, then we go to U to U via F, and then we again go from U to V via sigma. So we see F goes to sigma, F sigma inverse. So this is our species. We can't say it is a species. We also have to check functoriality. So I'll urge you to check functoriality for 3 and 4. Because it's not immediately clear why they are satisfying these functoriality, please take. It's an easy exercise though. So this was the species of permutation. So see, so permutations and linear arrangements, they have same, we'll later see they have same order, but their transport functions are very different. So we can, so therefore we see that in species of permutation, both the data are important, the sets that we are assigning and the transport functions. Next is species of cyclic permutation. This is also defined as we define our permutation with a little change. Here the set C, here it is sending U to a function f, which is a permutation, but which is also a cyclic permutation. And by cyclic permutation we mean, so if you have, so if you were talking about Sn, any cyclic permutation would have looked like this, A1 till An. So that is elements were forming cycles. So by cyclic permutation we mean that if U is consisting of this element U1 to Uk, we want a bijective function from U to U such that these elements can be arranged in a cycle. That is, we could pick any element. Say I pick some U2 or something. If I pick some U2, then it forms a cycle. So I should be getting a different image. That is, UI1 goes to UI2. This UI2 is going to UI3, which is different from UI1 and UI2. Now this UI3 is going to some UI4, which is different from UI1, UI2, UI3. Now, and we go on like this, and the last element, the image of UIK minus 1 UIK. Now this last element UIK, it goes to UI1. So in a way we have completed our cycle. U1 goes to U2, UI1 goes to UI2, UI2 goes to UI3, and this goes to UIK, which further again goes to UI1. This is what we mean by cyclic permutation. And transport function, since it is a permutation and sigma is a bijection, so transport function we will define as we have defined in 4, and this is again an exercise for you. So if sigma, your C sigma basically should go from Cu to Cv. So if we start with some cyclic permutation on U, say F, we are sending it to sigma F sigma inverse. So now we know from previous exercise, previous 4 question, because each of these were bijection, this was a bijection, and therefore it was a permutation. So we know that this is a permutation. It is an so in, I think last tutorial we showed that a cycle go to cycle. So in the same way you can see that sigma F sigma inverse will also turn out to be a cyclic permutation. So this function is well defined, and this is the transport function. So here also check functoriality. And the last example for this session is, last species is species of endo functions, which we are denoting by capital E. So as it says, so it is sending E set U to the set of functions on U. So now how it is different? Now we are saying that F is a function from U to U. F need not be a bijection. So any function here will be going in this set. And here also we see transport functions, the earlier transport functions will work. So now, so we have done this examples. So now, again there is an exercise. Define species of involution in similar manner. That is, give transport functions and check functoriality. Another example is that you can try is, which is used a lot, is species of derangements. and species of power set. So try defining a first, try giving all these two data, that is assigning a finite set to each finite set, and secondly a bijection to each bijection. Species of power set. Okay, now once we have looked at these examples, let's try to do some questions. So first question is, we have to construct exponential generating function for each of these species that we have discussed above. So first question is, we have to construct exponential generating function for each of the species that we have mentioned above. Okay. Hello Shashikan. Am I audible? Okay, so in the last 30 minutes we discussed what is a species and we looked at few of the examples. Now for the same example we'll construct the exponential generating functions. So first of all, what is the exponential generating function or generating function for species? It is a power series. It is a power series of type. It is a power series sigma of type f. That is, it is a power series f0 plus f1x plus f2 x square by 2 factorial and so on, where fn is the number of elements in fu. So let's construct this. So first was species of set. So species of set, so we were sending epsilon u was going to a singleton set. So we see singleton set with one element u. So we see that order of epsilon u is equal to 1 for all u. So the exponential generating series will be just sigma x raised to the power n by n factorial. N varies over all integers. N varies over all integers, and this is nothing but e raised to the power x. So first was easy. Then second was species of k set. So it was like a indicator function for k set, that it was sending any set with k elements to a singleton set with one element u, and rest of them were empty. So what is fi? So what is fi? It is the order of epsilon set consisting of n elements. So we see that it is identifying. It is indicator function for k set. So it is, the order is 1. Order is 1 if n is equal to k and 0 otherwise. So what will be the exponential generating function for this? What will be the generating function of these species, or exponential generating function for this? So all coefficient except the coefficient of k are 0. So for this power series will be just this. Then third was species of linear arrangements. So species of linear arrangements, it was denoted by L. So it was sending each finite set U to the set of linear arrangements Set of linear arrangements on elements of U. So what is this order of this? If U has say n elements, what are the number of ways in which we can arrange these n elements in a line? So we have basically n positions. So this is basic counting problem. Suppose n position. So we had n options for the first one, n minus one options for the second one, n minus 2 options for the third one. So it is nothing but n factorial. And generating function is for this species is Lx is sigma x raised to the power n by n factorial into n factorial, which is sigma x raised to the power n, which is nothing but 1 upon 1 minus x. Then next was species of permutations, and it was same as the previous one, because on an n element set the number of permutations are n factorial. So if you have a element from U to U, so here you can see we have these element U1 UK. This element has n options, this has n minus 1 options, and similarly it has just one option left. So number of injective and bijective functions from U to U are n factorial. Now next was species of cyclic permutation. So we have to find the order of C 1 to n. So if you have n elements, number of ways to arrange n people in a circle were n minus 1 factorial. And this in one tutorial we proved this using bijective counting. That using bijective counting by constructing a n to 1 function. Now last was species of endo functions. So number of functions from n element set to n element set. So this is also a basic bijective counting problem. So if you want to give a function from 1 to n to 1 to n. So you see 1 has n options. Since this function has no restriction, each image can be repeated. 2 also has n options. Each of them has n options. So each of them has n options. So the total number of functions are n raised to the power n. Okay, sorry. Here in the last example we had to give generating function. So generating function was this 1 factorial xn, which is sigma xn by n. and here the generating function will be, so Fn is n raised to the power n xn by n factorial, which is nx raised to the power n by n factorial. So this was generating functions for species. Next thing we did in species was we looked at the isomorphism type generating series. So now the next problem is, for the above example, construct the isomorphism type generating series for each of these species. So first of all, what is isomorphism type generating series? So given a species F, we can construct the isomorphism type generating series as follows. First of all, so it is so if it is a generating type series, so we are so it is of form Fn tilde x raised to the power n, and we are interested in looking at this number. So what is this number? So we are looking at the isomorphism type. So if in a sense, species of set this we have these various species of set, species of k set, species of linear order. So it was a rule which was denoted by some capital letters, say F. So fu, so we were assigning a finite set to each finite set u. So this fu, elements of fu can be seen as, are also sometimes called F structures on u. Now when we are constructing the isomorphism type generating series, we are interested in counting the F structures up to isomorphism. That is we want to define we want to first of all define the appropriate notion of isomorphism of two F structures, and then we want to count the number of isomorphism classes. So how do we do this? So first, for any integer n greater than equal to 0, so we are defining it for n, for each n. So we look at the F structure on any set u which has n element, and this n set has n element. So without loss of generality, we can take this set. Now we say that two structures on Fn, that is two elements of Fn, say u and v, they are equivalent if and only if we can find a bijection of this set n, which is sending u to v. So if this happens, we say that u and v are equivalent. And now you need to check that this is an equivalence relation. So clearly u is related to u because identity function send u to u. Now if you have a function u which is sending u to v, we want to construct a function which is sending v to u. So we can look at the inverse. So it is also reflexive. Now we want to look at the transitivity, and that will be done by composition. And here we will be using all those we will be requiring the compatible properties A and B. You'll see. So we see that this is an equivalence relation. That is, two structures on Fn are equivalent if we can find a bijective function which is sending the first structure to the second structure. Now we define this F tilde n to be the equivalence classes under this relation, and small f tilde n is the number of equivalence classes. And isomorphism type generating series is basically Fn tilde x raised to the power n, sum of Fn tilde x raised to the power n for all n. And Fn tilde here is referring to the number of isomorphism classes. So now let's construct this isomorphism type series for each of these series. So first, A is sets. So epsilon n was coming out to be singleton set n. So it has just one element. So we see, since it has just one element, equivalence relation is trivial, and therefore epsilon tilde n will also have just one element, and epsilon tilde. So the isomorphism type generating series will be nothing but 1 dot x raised to the power n, which is equal to 1 upon 1 minus 6. Now second B is K set, species of K sets. So here also epsilon n was singleton in case of n equal to k and empty otherwise. So we see it has either one element or zero element. So here also the equivalence relation is trivial. So we'll have that fn tilde will be equal to fn, which was 1 if n equal to k and 0 if n is not equal to k. So the isomorphism type generating series for this will be just x raised to the power k. Now the interesting examples start. So first is species of, so here you'll see when you're trying to calculate isomorphism type, since this equivalence relation is defined using those transport function. So here is what the transport functions make the difference. So first we see that species of linear arrangements. So species of linear arrangement. So suppose we take Ln. So it was basically all bijective functions from n to n. From n to n. So now by the f is related to g. Oh, sorry, it is a species of linear arrangement. So let's to make it simpler, so we can take any sets, like, so let's take this a1 an to be our set. So any linear arrangement is a function from 1 to n to a1 till an. Now we are saying that f is related to g sorry, L a1 an was this function, sorry, my notations are bad. So it is a set of function f from 1 to n, because we are basically seating till a1 an, f is bijective. So now we have to look at the transport functions. So transport functions, look at the transport functions. So if you had any bijection from a1 an to a1 an, f, sorry, this is sigma, yes. So what is, wait, okay, yeah. So we have to say when two linear arrangements are same, f is related to g. F is related to g if and only if there exists sigma, a bijective function from this set to this, such that the if we look at this function 1 to n a1 an and this function, so this is sigma, oh sorry, this is f this, so we want that this function should be equal to g, so we want to construct g. So we, our claim is all linear arrangements are isomorphic. So suppose you have a linear arrangement, this ai1 ai2 ain, so these aij belonging to a1 an, and we have another linear arrangement, this is my linear arrangement f, and this is my linear arrangement g, aj1 aj2 aj3 ajn. So if this is my linear arrangement, so what I want to do, I want to construct a function from this element, this set a1 till an, this set which is sending this linear arrangement to this linear arrangement. And when we were discussing this example, so the what is transport function doing? It is what is transport function doing? Transport function, so this sigma, so it is using sigma and f. So this sigma is this bijection is basically renaming the symbol, and f is giving a linear arrangement. So if we want to construct a function, we see that if we send ai1 to aj1, aj2 to ai2 to aj2, then sigma of will be g. That is, define sigma as follows. So here we have that fai, so let's call it af1, af2, fai is afi, and this is g ai is a gi. So the corresponding function is, we are sending af1 to aj1, sigma defined as follows, where af1 goes to aj1, af2 goes to aj2, and afn goes to aj. So we see that any two linear so we have shown the claim. So we see any two linear arrangement arrangements are equivalent. So here also we see that f and tilde will just turn out to be 1 for all n. So this was, so we see that all linear arrangements were isomorphic. Okay, now the next example is species of permutation. Species of permutation. So S Pn was a Pn is a function from n to n such that f is a bijection, and if sigma, suppose sigma is a bijection from n to n, What was P sigma? P sigma was defined to be going from Pn to Pn. It was sending F to sigma inverse F sigma. So any two if we have Fg two permutations on N, F is related to G or equivalent to G if and only if sigma F sigma inverse is equal to G, which is same as saying that Fg are conjugate in Sn. And in previous tutorial, in last tutorial or the second last tutorial, we see that they are same if and only if F and G have same cycle type. And we also saw that number of cycle types on 1 to n or on Sn were number of partitions on n. So species of permutations is nothing but the isomorphism type generating series for species of permutation is this Pn x raised to the power n. Pn is the number of partitions on n. When set. Now last is species of cyclic permutations. For this species also we see that C tilde n. So it is a subset of the above one. Oh, sorry. And we see that and the transport functions were same. So any two cyclic permutations will have same cycle type. One to k. Therefore, any two cyclic permutations are equivalent. Hence, here Fn tilde is 1 for all n greater than 0. And for n equal to 0, we have no cyclic permutation. So C tilde x is x plus x square plus x cube, which is x upon 1 upon 1 minus x. So this was for today. We looked at some species. We looked at like 5 species and we constructed first of all transport functions for them, then the ordinary generating function, or then the generating functions for them, and then also the type generating functions. So I haven't constructed So I haven't constructed the isomorphism type generating function for endo functions because it requires bit work, because so you can try it on your, you can try it. Okay, so this was all for today. Thank you.